Hello students, welcome to today's lecture. Today we are going to study the heat transfer part, okay? Or you can say energy transport, okay? First of all, we will study the Fourier's law of heat conduction, okay? So mainly in heat transfer, we have three forms of transport. One is molecular transport, that is by conduction. Secondly, it is convective transport, that is by the motion of the fluid. Thirdly, we have radiation, right? Radiative mode of transport. Okay. So in this course, we will basically deal with the conduction part and maybe with the convective part. Okay. So let's begin. So we have Fourier's law of heat conduction. It is basically nothing but conduction mode. Okay. So what is Fourier's law? So you already know this is small q equals to k delta t by delta x, right? Definitely there is a minus here. Okay, so what are the terms? This is nothing but heat flux. Generally, we write it watt per meter square or joule per meter square dot second, right? So it is energy. Joule is the unit of energy. Joule per unit area per unit time. That is the heat flux, right? Or joule per second is nothing but watt. So you can write in short like this. But generally, the small q means the heat flux. Okay. And what is K? This is thermal conductivity. And what is the unit? It is nothing but watt per meter per Kelvin. Okay. And what is delta T? This is a temperature difference. So unit of temperature is in Kelvin. Generally in Kelvin, the SI unit. Okay. Don't use degree Celsius. You can use degree Celsius, delta T in degree Celsius only if the thermal conductivity is given in per unit of degree Celsius. Okay. If the thermal conductivity is given in per unit Kelvin, then you have to use the temperature in Kelvin. Okay. And delta X, it is nothing but the distance. So it will be SI unit will be meter. Okay. Also in some books, it is written as Q is equal to Ka delta T by delta X. See, the area term over here was shifted to this term, right? That means this Q is nothing but heat rate. So it is nothing but joule per second, or it is watt. Okay. It is no more a heat flux. This is heat rate. Okay. Watt or joule per second. Because area you have multiplied over here. Okay. Same form. Okay. So when we say heat flux, you have to use this one. Okay. When you want to find heat rate, then you can use this one. Okay, so Fourier's law is basically given in terms of the heat flux. So this is Fourier's law, not this one. Okay, so this one is a derivation from this one only. Okay, so this Fourier's law, this law was for delta x. So in one direction, that is x direction. What will be this in the y direction? Simply replace delta t by delta y. Okay, what will be in the z direction? That is the delta d by delta z, right? And so on. So what if the heat is transferred in all the directions? So then the q will be a vector, right? So you have to sum all it up. Okay. So this you already know it. Okay. So let's go through the textbook. So how the Fourier's law of integration was concluded. I mean, how it arrived to this formula. Okay. So how this formula was arrived. So assume we have two plates, right? This is solid plates, and we have a, this is slab actually. This is slab, and this is the top plate. This is the down plate. Okay, these two plates are separated by a distance y. Okay, y as given here. Suppose this plate is at temperature T naught at T time equal to 0 initially. Okay. Yeah, this surface will be T naught everywhere. Okay. Here. And here we have the another surface. Suppose you bring this surface at T1 temperature, what will happen? Let's say T1 is greater than T naught. Definitely heat transfer will take place from higher temperature to lower temperature, right? So if this is there, so heat transfer will happen in this direction, right? So initially the top surface was at T naught, right? And suddenly I have increased the temperature of the bottom plate at T1. What will happen? Now heat will try to flow in this direction, right? So this heat will flow in this direction until there is a equilibrium is attained, right? So you can see this graph, so how temperature is changing, right? So at after small interval of time, so what will happen? The profile will look like this. So this is at this surface is at T naught temperature. This is point is at T1. I mean, these all points are at T1 and all these points are at T naught. Okay. So what will happen there? The in between these two plates, there will be some temperature change in between. So this the close points which is close to this surface will try to increase, right? So it will try to the temperature will try to increase a little bit. So at equilibrium, after very long time, what will happen? The temperature inside the slab will have like this. Okay, this means this is just a temperature profile. Okay, this is like temperature versus distance. Okay, so it is saying that this profile is like this. In actually, suppose this is the slab, what it means is this plate is at temperature T naught, this whole points at T1, right? And this will be at somewhere in between this T naught and T1 temperature, and this, right? So if you see now compare this to graph or this one, these two. So at y equal to 0, what is the temperature? T1, right? Y equal to 0, temperature T1. At y is equal to this distance, that is capital Y, what is it? T naught, right? What about in between these two? So if you check this point, so at y is equal to, let's say half point. What is the t value? So t is something between average between these two, T naught, so on. So from this experiment, we can easily conclude that this is true. Okay. So Q is nothing but heat rate, A is area. So here it is now rewritten in the form of small q. Okay. Small q means heat flux, A is thermal conductivity, and dt by dy, the gradient. See this small qy. Qy means heat is getting transferred in y direction. In this example, this was y direction, so it is transferred in this y direction. Okay, similarly, if it is in 3D, heat is transferred in all the three directions. You can have qx, qy, qz. Only the difference is the gradient direction, this direction. And in vector form, you can write this q Bold means this is a vector. In while writing, you write like this, okay, on paper. So while writing this, you can write like this, K, and you know this is nabla gradient tail operator, and T is a scalar, right? So if you take the gradient of temperature, that will become vector, and that's why this is also a vector. Okay. Now this is a assumption that K is constant. K does not change, is not a function of the direction. Okay. That means K is constant. It is assumed that K is constant. And the K is constant for the materials called isotropic. So isotropic materials means some property like thermal conductivity is same in all directions. Okay. If let's say it is y, this is x, this is that. So this K will not vary in this direction, not vary in y direction. It will not vary in z direction. So K is same in all directions. That's why this K is constant in this example. But if you have non-isotropic means the property will be different in different directions. Okay, if you take the thermal conductivity in x direction, it will be different. If you take the thermal conductivity in y direction, it will be different than x. Right, so those materials are called non-isotropic. So for non-isotropic materials, we have to use different equation. This one, right? So this is not in our syllabus. So if you want to know more, you can go and read about it. So this kappa, now it is kappa. This is nothing but a symmetric second order tensor. Okay, this is called thermal conductivity tensor because the material you have chosen is non-isotropic. That means the thermal conductivity will change in different directions. Right, so you can use this equation for non-isotropic. But in this course, you will only use this equation. You will assume that the thermal conductivity is constant. Okay, it is for isotropic material. Okay, and in Fourier's law, you have small q is equal to minus k. Let's say you are taken in x direction. K is thermal conductivity, right? But if you want to compare this Fourier's law with the Newton's law, then you have to use the thermal diffusivity, right? And I have already shown you. So you have to divide by rho Cp and here multiply with rho Cp. Then only this is nothing but heat concentration gradient. This will become heat concentration per gradient, okay? Or per unit heat per unit volume divided by the distance. Okay, this term is called thermal diffusivity alpha. So you can see here is equal to Cp cap. Cp cap is the specific, right? So what is the specific unit? Joule per Kelvin or kg Kelvin. So this is nothing but specific heat capacity. That's why it is cap here. Okay. Otherwise, you can just write Cp, that is Joule per Kelvin only. Also, you can know the ratio called Prandtl number PR, that is nothing but mu Cp by K. Right? So you can rearrange this mu by rho and K by rho Cp. Okay? The rho cancels out then ultimately. So this is nothing but momentum diffusivity, right? Or you can say kinematic viscosity. This is thermal diffusivity. So Prandtl number is nothing but the ratio of momentum diffusivity and the thermal diffusivity. Right? So what Prandtl number says? Suppose Prandtl number is greater than 1. That means if this is greater than 1 means thermal conductivity is less than this one, or you can say momentum diffusivity is greater than the thermal diffusivity. That means the momentum transfer rate will be higher than the heat transfer rate. Okay, so you can neglect if this Prandtl number is very greater than 1, you can neglect the heat transfer. You can assume that it is purely momentum transfer. Similarly, if Prandtl number is very less than 1, you can assume that only heat transfer is taking place. There is no momentum transfer or fluid motion. Okay, so you know this, and there you also know Peclet number. It is nothing but Reynolds number into Prandtl. Now, okay, we will go to the units once again. So this is nothing but heat flux. Joule per second is watt, and per meter square, that is nothing but heat flux. Okay, this is in Celsius, this is in British units. Temperature can be Kelvin, in SI unit, Celsius, it is Celsius. Y distance in meter, centimeter. This is thermal conductivity, watt per meter Kelvin. Specific heat, joule per kg per Kelvin, right? And this is thermal diffusivity. Thermal diffusivity will be in meter square per second. Momentum diffusivity is meter per square. Mass diffusivity is meter square per second. They all are same. This is dynamic viscosity. Dynamic viscosity. This is Pascal second or kg per meter second. In Celsius it is gram per centimeter second. And Prandtl number is dimensionless. No units. Okay. Now let's study the variation of thermal conductivity with temperature. Okay, so generally we assume K is isotropic. It does not change with the distance. Okay, however, K is a function of temperature. Okay, generally you assume while solving Fourier equation, you assume that K is constant. It is not a function of temperature, nor it's a function of the direction, right? So it's a constant. So, but isotropic material means the K is same in all directions. That doesn't mean that K is not a function of temperature. In fact, K is a function of temperature. So let's see how the temperature varies for different type of materials like liquid, gas. So you can see from this graph also, this is I think some liquid, right? All are liquid. But let's see the graph. Okay, so this graph is between the reduced temperature and the reduced thermal conductivity. So don't worry about the reduced temperature. This is done to make it dimensionless. Reduced temperature is nothing but T by critical temperature, and the reduced thermal conductivity is nothing but Kr by K by Kc, that is thermal conductivity at critical temperature. Okay, so we have saturated liquid in this curve, and this line is nothing but your saturated vapor. So you can say this line is basically for low density gases, and you can assume this is for liquids. As you can see, for gases, this is the line. So I am talking about gases. Okay, so as the temperature increases, the thermal conductivity will increase for gases. Okay, and what about liquids? Liquids, as the temperature increases, the thermal conductivity will decrease. You can see here clearly this is decreasing with increase in temperature, right? So remember this. Okay. The same thing is given here also. What about thermal conductivity of solids? Thermal conductivity of solids are generally hold constant. Okay. Thermal conductivity is taken as constant on the metals. You know effective thermal conductivity of composite solids as you have derived in the heat transfer course. So let's study the convective mode of transport of energy. You also know that Newton's law of cooling, right? So that is nothing but heat flux is nothing but H delta T. Right? This is Newton's law of cooling. This is mainly used for convective transport of heat energy. Okay, but generally we can write this is convective mode of transfer for energy. So we have this term is kinetic energy, rho v square. This is all are in the per unit volume. Okay, everything is per unit volume. So half rho v square is kinetic energy per unit volume. Rho u cap is internal energy per unit volume. Okay. So u cap is nothing but specific internal energy. So internal energy per unit mass and rho cancels out. Then this will only be internal energy per unit volume. And v is the fluid velocity in the x direction, right? And d is the surface you have taken, okay, over which you are calculating the heat flux. Okay, so this is the convective mode of transfer. This is the formula. So in all directions, what will happen is you have to just simply replace vx by vy and v by vz. Right? So in general, you can write this one. If the convective mode of transfer is happening in all the three directions, so it is the kinetic energy per unit volume, internal energy per unit volume, and the velocity vector. That means the convective energy flux vector, okay, in all directions in 3D. Okay, so in next class we'll study the energy balance equation. Okay. So you will also see the equations of energy, how to use them while solving problems. Okay. Also, you can derive the thermal conductivity of composite wall and so on. There are other examples. Okay. Thank you.